Hey everyone, thanks for having me, and especially at 7:30 in the morning. Our grand rounds are at noon, so like, you know, people could not do this. So thanks, Greg, for the introduction. I'm a cardiologist and an imager at UCSF. Can you guys hear me? Okay. I run a research lab where we're developing machine learning methods to improve biomedical imaging, and I'm an echocardiographer and CT nuclear trained as well. But today I want to tell you about the research. I want to tell you what we're doing and also what remains to be done to bring the science and medicine of imaging into the future. So we're going to cover a lot of ground today. I'm going to highlight some fundamental problems with imaging the way we practice in the clinic these days. And I'll explain why I formed my lab to tackle these problems as new computational tools became available, principal among those deep learning. I'll tell you some specific use cases for deep learning in cardiac imaging from my lab. And then finally, we're going to step back and look at this field from a bird's eye view and understand what's needed from a programmatic perspective to take us further. So imaging today. I don't need to tell this crowd that in medicine, imaging is more than 1,000 words. It's key to diagnosis and management, not just in cardiology, but across medicine and across modality. It's deceptively easy to learn, but takes a lifetime to master. And nowhere are those things more true than in cardiac ultrasound, where we're imaging structure and function in real time. This is an example of an image. I was telling Dr. Otto about this yesterday. This is an example of an image that would have meant nothing to me my first day of fellowship. And now it tells us, what we're looking at, what the valve is, what the problem is, something about the severity and the mechanism. So we also know that many times the report is not the truth. This is from a patient who came to see me in clinic for a CAD evaluation because his father had just died of MI. And I looked at his ECG and it had T-wave inversions without a good explanation, no LVH or anything like that, no hypertension. He had had a previous echo, and I don't know if you guys get this, you guys have some tech around, but in Silicon Valley, you get followers of the quantified self movement. So he comes in with 12 years of LDLs on his iPhone. He had his grandfather's telemetry strip. I don't know what I was supposed to do with that. But he also had his echo report. He said, "Doc, I've had an echo and it was normal, and here's the report." So he was very confused when I ordered another echo. We couldn't get the old images. And indeed, we found a pretty subtle, but we found a subtle apical HCM that we later confirmed on MRI, and his brother had the same thing. So the report is not always the truth. We also know that sometimes only seeing is believing. Sorry, this seems to have some, I never noticed that, it has some volume with it. But this is a patient, maybe I stop it so it doesn't keep doing that. This is a patient who came in short of breath when I was on service. I met the patient while this echo was being done, so I was seeing both of them and this heart at the same time. And what strikes you immediately is that there's clot in transit and RV dysfunction. I'll play this thing. Oop, no, I'm giving it away. Here we go. But what you'll also see, let me see if I can. But what you'll also see is that there's stuff on the left side of the heart too, on the mitral valve. And so then you say, how did that happen? And I figure there must be a PFO and there must be clot in transit across the PFO as well. So I called one of our surgeons. He's an excellent surgeon and a friend of mine. And I was explaining this to him, but I could tell, over the phone, he just wasn't quite grasping what I was saying. And he was still thinking, like, why isn't this just a case for IR? So we got a TEE, which you now saw. And I paged the surgeon again, and I said, come, you have to see this for yourself. And this is what we saw, which is indeed a rope-like clot in transit across a PFO between the atria. This was acquired by one of our excellent fellows. So he came in, he saw this, he went silent, he walked away. We were kind of wondering, well, what's going on? He was already on the phone booking an OR, and the patient did fine. So we know that in medicine, only seeing is believing. So for all these challenging and complex cases in imaging, today we are the best tool that we have to acquire and interpret medical imaging. For echo, that's a sonographer acquiring the images most often. and an echocardiographer who samples from the image they see, computes on it in here, thinks about it, and then outputs what they saw and what they thought into a communication with someone else, a text report or a phone call. But to err is human, and I can say that because I'm one of those humans and I read in the lab once a week. We can be inaccurate, especially when the finding is rare or subtle. Our reads might not be completely reproducible from one reader to the other or one day to the next. We have trouble measuring even simple things sometimes, like chamber size and mass. And then there's some things that are really hard to quantify as well, like spade-shaped LV and diastole. You know, how do we get to quantify stuff like that? And then finally, we humans get tired after a while. We can only read so many images in a day. So these are significant shortcomings in image-based phenotyping, and they can't stand. We need more for echo and across medicine. We need accuracy and reproducibility, and we need that delivered on a population level, speed, and scale. Why is that? We've recognized that inaccuracy and variation in imaging can contribute to overall medical error. And overall medical error is the third leading cause of death in the United States. And we also have precision medicine goals for high resolution genotype phenotype mapping of various million-person cohorts, million vets, all of us, so forth. But in precision medicine, I've met with some of you guys this week and told you your genotype is only as good as the phenotype you can map it to. So if we want to get the most out of these million-person cohorts, we need to be able to leverage some of the information-rich image-based phenotypes as part of the precision medicine research. And then, okay, you sequenced, a million people, who's going to read a million echocardiograms or MRIs or CTs? Even if cost wasn't an issue, the scale of that task alone is superhuman. So there's at least two good reasons that we need a better way to approach biomedical imaging. That brings me to this. What if instead of the status quo here, we could analyze all the primary imaging data, and you're not sampling, I see something different in that image than you or you. We could see all of that data, or if we are sampling, we're doing so in a reproducible fashion. We are able to think about that image in an accurate and reproducible way and use all the data at our disposal for phenotyping. And what if we could do that at a scale that does not tire? So that's what I call precision phenotyping, and that's where imaging needs to go. And when you hear that, you think that's what computers are designed to help us with. So that leads to the central hypotheses of my lab. One, that machine learning can be used to analyze medical imaging with related, text and related data, to decrease diagnostic error, and to scale image-based phenotyping for precision medicine applications and potentially novel discovery. In my lab, we use a lot of deep learning or neural networks because they've proven especially good at finding patterns in imaging. So has anyone here done deep learning and neural networks? Any? Okay, some, good. I'm going to take you through a quick anatomy of a neural network, and this is, cartoon. So this is, neural networks are loosely modeled after the way neurons connect in the brain. That's where they get their name. So here's a cartoon of a deep neural network. This collection of blue circles, each blue circle is called a node, and a node is akin to a neuron, if you're taking the analogy. These nodes are all connected. That's how you get the word network. And then we arrange these nodes in layers and we stack them. And if you have a lot of stacked layers, you get the word deep. So that's how you get the words deep neural network. And if you remember, traditional algorithms apply rules that we make up to data. Machine learning algorithms learn patterns from data. So that's really the distinction between traditional algorithms and machine learning algorithms. And this neural network, it's like the brain of a newborn baby. It's wired to learn, but it doesn't know anything yet. So we have to feed it some data. This learns patterns from data. So we have to feed it some data so it can start learning patterns, and that's an example of supervised learning. So we take an image, we break it down into pixels, we feed those pixels into the neural network. Each node in the network takes in some information, computes on it, and outputs some info. Those outputs are weighted, right? A million little voices have an output. Those outputs are weighted and synthesized across the network into a prediction, that green thing. And the prediction is then measured against the training label to see how good the prediction was. Now that training label can be something literal, like I could put a picture of a ventricle and the training label says ventricle. Or it could be something a little more abstract, like I put in a picture of a ventricle and the label says Timmy wrist sore 3 or diabetes. And that's one of the powers of what we're able to do with these. And we just keep giving the network more training data with more training labels. And the network keeps computing on the new data, and it keeps comparing its prediction to the training label. It keeps adjusting its weights again and again and again and again. And along the way, different layers in the network might start to see different image features. So early on in the network, that layer might be seeing vertical lines. Maybe a little deeper in, sees diagonal lines, something more complex. And the deeper and deeper you get near the end of the network, maybe it's seeing a high order image feature like a ventricle. And that's how it gets its decision. And this process of being able to see image features, that's what makes neural networks work better for images than other types of machine learning. Other types of machine learning, never really get to see an image as anything more than a collection of black and white pixels. But neural networks are helpful for this. So you keep training your model with more and more data. And then finally, the network is trained. And then you can give it a never before seen test data and evaluate its prediction performance. And just like you can have neurons that are excitatory or inhibitory, or neurons with different neurotransmitters, there are different nodes with different functions. And so the nodes that you choose and how you connect them together allows us to build neural networks for different kinds of tasks, not just the example I showed in the cartoon. So I've presented some lofty goals. I've said imaging needs to change and computers are amazing. But in research, we still have to put our pants on one leg at a time. So now I'm going to drill down and show you 2 specific examples of exactly how we've used deep learning as one component of the scientific process. Although our work applies across modality and across medical specialty, we started with cardiology because I'm a cardiologist. And we started with ultrasound because it's really the everyman's imaging modality. It's a great balance of information richness and clinical volume. And it's radiation-free, relatively cheap, and the hardware is moving towards a handheld point of care, which means that the software has to move in that direction as well. Also, because echo is used for diagnosis and management of pretty much every cardiac disease, and sometimes some non-cardiac diseases like sinus tachycardia and so forth, there's little selection bias in large echo data sets for the types of patients or types of diseases that you find. So there are several advantages to studying echo, but there are challenges as well. Compared to things like CT or MRI, echo is noisy and grainy, and a single ultrasound study is actually it's not just a stack of images like a CT stack. It's a collection of multi-modal images that are acquired freehand by sonographers. You guys know this. One ultrasound has many videos, many still images, M-mode, 2 kinds of spectral Doppler acquired from peristernal, apical, subcostal, and suprasternal positions. So 15 views in a TTE alone, and this is not even an exhaustive catalog. So view classification emerged as a foundational task for computational analysis in echo, and really any ultrasound. And so the first question we asked was whether we could train a deep learning model to classify among those 15 standard transthoracic views. We randomly selected 267 echoes from our clinical database. We anonymized them. This is important. We shrunk them. Where there were videos, we chopped up the video into image frames. And so we fed image frames to our model. We split the data into training set and testing set. We split it by study so that we maintained sample independence between training and testing sets. And we used a pretty simple convolutional neural network, similar to what I showed in the cartoon. This one was inspired by BGG16, which was an ImageNet winner at the time. And the model was able to learn transthoracic views. These dots are input images, color-coded by view. And you can see that in their raw form, they don't cluster very well. But after the last analysis of the last layer of the neural network, you can see that the views, the images do cluster by view. So now we're going to look at the performance on holdout test data in a little more detail. This is a heat map or confusion matrix designed to compare the actual view labels on the y-axis with the model predicted view labels on the x-axis. So perfect performance would be 100% dark blue boxes right across the diagonal. And the model does pretty well, about 92% accuracy. That was very fast, which was important if you want to integrate this into clinical workflow in the future. And it was better than board certified cardiologists on the same low resolution, low context task. With a simple majority rules vote on related image frames, we were able to reach an overall accuracy of 98% on the video views. And most often we saw clinically relevant interpretations behind the model's confusions. So here, the model confused the RV inflow view for an apical two-chamber view about 14% of the time. And that's not a mistake we would make in real-life native resolution video. But it does suggest the model was seeing an atrium and seeing a ventricle. It just mistook the right heart and left heart. When the model was correct, it was very confident, and when it was incorrect, confidence ranged widely. And that's what you want from a practitioner as well, to know what you know and not be falsely confident when you don't know. So those were some of the novelties of what we've done. But also a major theme in my lab is to push the limits of performance with real world data, with minimal data, and to figure out how to add some interpretability or validation to the model performance. And that's important, and I've had this discussion with some of you guys this week. You know, neural networks, the more data they get, the better they can do. But with cat videos, that's fine because we've got millions upon millions of those. When you want to use neural networks for medical problems, you want to use them for some of the problems that are hardest for physicians. Some of the problems that are hardest for physicians are hard because we don't see them often, because they're rare. And so if we want neural networks and machine learning to have impact for us as providers, we're going to have to make these things work for rare diseases as well as cat videos, and on real world data, which is not always beautiful, not always textbook acquired. So we did use real world data in terms of demographics, as well as indications, as well as vendor agnostic real world image variation. So this is an example of a parasternal long, all these are parasternal long axis category, whether they changed in zoom or depth, use of dual mode or color Doppler, etc. And at that time where everyone's talking about big data as if it always goes hand in hand with machine learning, we sought to find the minimal data set for solving the task at hand, and that's inspired by fellow training. So these were the COCATS requirements for Echo. So any one of us is expected to definitely know the views as well as basic pathologies, reading just a couple hundred echoes. So if we build a model for view classification that needs millions of echoes, have we really accomplished anything? Maybe, maybe not. So this is a graphical representation of the data that we used for our study. 267 studies from our overall database. Then we shrunk them, and then we actually took the monochrome color slice. So yes, in this study, we only looked at views, but we were able to predict views with less than 1% of 1% of the data available to us. And that has important implications for applying these methods towards study of phenotypes or diseases that may be rare in the population. And I'll show you that in just a bit. Finally, we did some work to interpret our model's decision-making. That's an area of active research in machine learning, but we did what we could. So with occlusion experiments shown here, we took our test image data set and we covered it with gray masking boxes of different shapes and sizes, and then saw how was the model able to predict on masked images. And we found that prediction performance really plummeted when we covered the heart itself, meaning that at least the model's accuracy depended mostly on cardiac structures. And that seems like a no-brainer for us, but for a computer, it did not have to be that way. We also performed saliency mapping, which means that for a given, for a given input image, we asked the model to plot the pixels that were most important to it in making the decision that it did. So here's two examples of an input image and the saliency map. And so we can see from the saliency map of these two examples, a human echocardiographer can recognize a parasternal short axis with a mitral valve in the middle. We can recognize an aortic arch structure shown in dual mode. And so at least it shows that the pixels that are most important to the model are also ones that create familiar structural outlines to us. We decided to challenge the model on an image type it had never seen before. These are two examples of X-plane views, and you can see why I did not include these in the training set. You get the image and its orthogonal view in the same slide. So how do I label this? Is this a 4-chamber or a 2-chamber? Is it a parasternal long axis or short axis? So the model had never seen these before. It's not just holdout test data, it's an entirely novel class to the model. And the model still guessed correctly most of the time, although notably the wide confidence intervals for these guesses reflected that this was a new kind of image type that had not trained on before. So that was the first paper. That's how we got started exploring a bunch of fundamental questions, applying deep learning to medical imaging. And like I said, view classification is just the first step of a comprehensive platform that we're building, from infrastructure and foundational tools to classification of views to diagnosis and composite diagnosis from different data points. And then we'll hope to get to novel phenotypes, higher order analytics, and of course, bring all of that back into the clinical workflow. So we're going to work midway up this pyramid now. I'm going to show you one more concrete example from the lab, which is where we wanted to see whether we could find diagnostic signals using deep learning, not just view classification. So for that, the first case we looked at was prenatal detection of congenital heart disease. Prenatal diagnosis of CHD has been shown to improve outcomes, and fetal ultrasound can detect most CHD lesions. It's in their guidelines. So, you would say, why is this still a problem? Isn't this solved? Everybody gets their 20-week ultrasound and we can find 90% of complex lesions. But the major problem here is that in practice, the fetal diagnosis rate is about 30 to 50%. It's not just because people aren't getting their ultrasounds. And the specificity is also about 40 to 50%, depending on the lesion. So this is an example where we have an imaging modality. It could do the right thing, and it's not. So why do we have this surprising gap between the possible and the real world? Quality control research suggests that this gap is due to technical factors, small heart and a moving fetus, things we don't have to deal with as much. But most importantly, it's because CHD is rare in the population. So it's hard for a physician to build and maintain their skills for CHD detection. We asked whether deep learning models could improve upon commonly reported CHD detection rates. And the most fundamental questions we're asking with this study are, how do we scale and democratize expert ultrasound diagnosis? That's what we're really asking. How do we facilitate clinical adoption for our computer solution? And how do we leverage traditionally data-hungry neural networks for a rare disease where there's just not a lot of data, no matter how widely you cast the net? And how do we do this for a task that challenges even trained physicians? So we took an approach here that I'll call using clinical priors to kill two birds with one stone. Basically, instead of using the entire fetal study as an input to our model, thousands of image frames, we made use of the clinical guidelines that specify these 5 screening views of the heart that are supposed to be able to detect most complex CHD. And then we hypothesized this would allow us to find diagnostic signals for rare diseases by using a much smaller data set. And it would be founding our model on the important clinical work that's come before to aid in adoptability for that reason. And because we had such a small data set for our adult view classifier, that's what gave us the sense that we could achieve this. For this study, this has improved over time, but this is where we were at the time. We've used 685 retrospectively collected fetal echocardiograms, all at screening age from machines from multiple vendors. We used about 500 normal studies and about 100 each of tetralogy of Fallot and hypoplastic left heart syndrome. We excluded significant non-cardiac abnormalities. And we broke this problem down into several steps, an ensemble of steps, different models. First, we trained a CNN similar to what we did before to find those 5 cardiac views of interest. Second, we developed binary diagnostic classifiers to determine for each view, is that view normal or not? Step 3, we used those per view diagnoses to create a composite diagnostic classifier. Is the heart overall normal or not? And last, we're using fully convolutional networks to calculate some of the standard fetal biometrics that are used, with the ultimate goal of including them in our composite score. So step 1, the view classifier. Here's our confusion matrix. AUC curves, we're doing pretty well. I showed you this with the adults. We won't go into it. We then trained and tested 3 different binary models to distinguish between normal versus tetralogy, normal versus HLHS, or normal versus either lesion. And on these ROC curves, each colored line is one of those 5 views. You can see that certain views have a higher C statistic than the others. Specifically, abdomen has a particularly poor C statistic for distinguishing. And what's interesting about that is that that's consistent with the clinical observation that the abdomen view is not supposed to be able to distinguish among these sets of congenital lesions. So it suggests again that the model is making decisions based on relevant image features. We also did occlusion and GradCam and saliency and so forth, but I showed you before. I'm not going to show you again. So then we come to step 3, the composite diagnosis score from those per view decisions. So we selected the views that had C statistics greater than 60. And for those views, if the image was normal, it got a 0. If it's abnormal, it got a 1. And those per view diagnoses create a vector. We embed these vectors in Euclidean space, and we took the Manhattan distance from the origin as the composite score, since a normal heart should be a vector at the origin, should be 0, 0, 0. And if that composite score was 2 or greater, we called that heart abnormal. So here we took a rules-based approach to our composite classifier at this time. Using this model, we came to the following sensitivities and specificities for tetralogy, HLHS, or either lesion. And this is far from perfect. We don't include all the complex CHD lesions in this work. But already on just one center's data set, you can see that we're beating common detection rates for these lesions reported across several studies in the community. We're also training models to calculate cardiothoracic ratio and cardiac axis by training UNets, so fully convolutional neural network, training UNets to segment anatomic structures. And this chart shows Jacquard indices for the different structure classes. So before I showed you a neural network that classifies images into different view classes. Now UNets classify pixels into different anatomic structure class. Is this pixel a heart? Is this pixel a spine? Is this pixel a chamber? And this just shows how well the model predicted shapes overlap with the human labeled shapes. So cardiothoracic ratio, normal is about 0.5. And you can see that we have good agreement between the clinically measured CTR, the training label, and the model prediction. And we have that across normal and CHD lesions, and that's consistent with the literature. For cardiac axis, a normal cardiac axis is about 45 degrees. And similar to published studies, our model predicts cardiac axis to be increased in tetralogy of Fallot. So in this project, we showed that combining clinical insights with ensemble learning methods can facilitate data-efficient strategies to improve diagnosis for clinically relevant use cases, even for rare diseases. And on both of the projects I've shown you, there's still a lot of work to do, a lot of work we've done, and I hope to show you that in the future. But since we've published these, people have started to get excited about deep learning, work from our lab and from others. And that's really nice to see. And now if you search the literature, you'll find many, many papers trying to apply neural networks to various medical data sets. But frankly, a lot of them follow a very similar path. It's we had data, we apply network, we report AUC. And the level of rigor and clinical utility to a lot of these studies varies widely. And that started to get me thinking, how are these single papers going to start coalescing into new knowledge for our field? We're going to need to take a programmatic approach to computational imaging, an approach that sets broad goals for what we can achieve. So we move past just trying to recapitulate what a human can do. Sets guidelines for rigor in the field. So we have to think about what the pitfalls are right now. Going backwards. And that's going to take building infrastructure and breaking down certain silos that are traditional in the imaging field. So I want to talk about a couple of those things. First, what are the goals of computational imaging research beyond this formula of data set network AUC? How are we going to mature this field? What's at the top of this pyramid, right? So here's some ideas. It's certainly not an exhaustive list. The first is obvious. We want to improve diagnosis, especially in the community, especially for rare diseases, for diseases that present with non-specific signs and symptoms, and for diseases that are difficult to detect until late in their course. The Fetal Heart Project is one example of that. Nope. Don't know why it's doing that. We want to be able to run real-time analytics within and among medical centers so we can measure image test usage, diagnosis, and quality. And we want to use this to decrease repeat testing, decrease the prevalence of non-diagnostic studies. And frankly, through this process, we're also going to uncover the true prevalence, variety, severity, and impact of errors in what we do in medical imaging. Only a small amount of errors lead to adverse events, which is usually the only way we find out that an error has happened. And we'll be able to build more accessible and more complete teaching and training libraries for our trainees and for ourselves in continuing education. Second, a computational approach can help standardize image-based phenotyping, both for clinical research, clinical registries, and also for basic research. It's going to change, I think, the role of core labs in clinical research. And also in the basic science, I have a colleague where they're doing mouse ultrasound, and the graduate student, in addition to doing their hypothesis-driven research, also has to basically learn to be a mouse sonographer. And that shouldn't be a limiting factor to the research that's being done. Clinical research studies are costly. It would be great if we could find a set of core phenotypes that no matter what clinical registry you're building, whether it's a podiatry registry or a heart attack registry or anything, there are certain core phenotypes that that you should get, so that then you can pool your registries around those core phenotypes and harness their power for future research. Finally, precision phenotyping can change how we measure health and disease. So I gave this talk once and someone said, that's great, but how important is this really? All the basic stuff that we measure is pretty accurate and pretty robust. And here are the ASE chamber quantification guidelines, and I've paraphrased this a little bit for brevity. But the authors themselves are still struggling with how to define simple things, common stuff, chamber size, right? Normal and abnormal. And here they say, the way we do things now, which is binning our sizes into small, medium, large, or mild, moderate, severe, does not account for the fact that many physiologic measurements in imaging are not normally distributed. And they say the better way to do this is to peg measurements as percentile values against a population of all comers, healthy and diseased. And they say, we haven't done this yet because the data doesn't exist. And I would add the analytics aren't quite there yet, but they will be very soon. If our imaging measurements are more precise and more accurate, we're going to be able to use them more confidently in mathematical analyses to find new patterns and structure among them, and perhaps lead us to better understanding of subtypes of disease as well. Computational analysis could lead to novel phenotype discovery because our imaging might contain more than meets the human eye. The same analogy when I saw, MR from MVP on that M mode first day of fellowship to now, there was information there that I didn't appreciate before. This paper is from Poplin et al. They're studying retina images for diabetic retinopathy. And that's great. They can predict, smoking and age and a bunch of hypertension, a bunch of stuff. But what I thought was interesting is they could predict gender from the picture of the retina. And that's something that an ophthalmologist cannot do from this image alone. So those things then remain to be validated and tested. And in fact, I co-lead a team as part of the Chan Zuckerberg BioHub, where we're using computational analysis as part of and clinical imaging to generate new hypotheses about the genetic basis of cardiac structure and function. We're excited about this work. It's a multi-center, multi-modality, multidisciplinary collaboration, and I hope I'll be able to tell you more about that in the coming months. So in many ways, I hope deep learning won't just recapitulate what we humans can do now, but will really push us forward. But as this new field develops, the research community is becoming aware of several potential pitfalls in research design and rigor. With several colleagues in the field, we're actually publishing soon a standards and reporting guideline for machine learning research and imaging. And there are other issues, so we'll chat a little bit about those. Training and validation in deep learning relies on a robust gold standard or ground truth label. And one thing we're finding is we have to think again about what is the ground truth. So I breezed by this earlier. This is the confusion matrix for our fetal heart views. And you notice there's a fair bit of confusion around those two views, 3VV and 3VT. They're just two slices of the heart. And what's interesting is the model's confused, but so are the experts. So one of my colleagues is on the guidelines committee for fetal cardiology, who defines what these screening views should be. And they shared with me an email thread that was specifically about this question of what image should constitute a 3VV and what image should constitute a 3VT. And I'll never share somebody's emails because you don't do that, but any guesses on how long this email thread was? Okay, it was 42 pages. 42 pages on just the difference between those two views. So from deep learning, two things are going to happen. One, computational models are going to help show us where we disagree and maybe push us to find consensus in new ways, maybe push us to define things in different ways. And then also this idea of gold standard label, ground truth label, is going to give way to a consensus label. We're going to have to, our models are going to have to be able to allow some uncertainty, some wobble in how we label things. So those two things will happen. Next, a word on multimodal data. So certainly we hypothesize that cross-modal data it has the opportunity to give us better results. You want to see the echo and the nuclear scan, or you want to see the ECG and the CT cross-modal. So I was asked a while back to be in a Kaggle competition, like a machine learning competition, where this was the challenge. So they said, come work on our competition. We've got over 500,000 cardiac ultrasounds and multimodal data, and your job is to predict coronary artery disease. So I said, okay, let me look at what data is here. So they have this picture of the heart, this picture of the heart. They give us this multimodal data, and then people are doing well. The best competitors are getting AUCs of 0.7. And there are a couple problems with what I've shown. Does anyone want to shout them out? Correct. So one of the pictures of the heart is a kidney. So that speaks to the true importance of good data curation and cleaning. And what do you guys think of this AUC of 0.7? It's basically, you know, the Framingham risk score, right? So if you're going to use multimodal data, you need to strive for effect modification. The combination of modalities, in this case, structured data and imaging, has to perform better than the sum of its parts, or else, you know, what are we doing here? And these are the kinds of things that it takes some clinical domain expertise to ferret out. Neural networks do not save us from our biases. My favorite headline for this is what happened when Microsoft's chatbot tried to learn from the Twitterverse and turned out to be a less than open-minded individual, we should say. But Tay became what she heard. And in medicine, it's this kind of bias which exists. This is from several years ago now, where in the New England Journal, they found that women presenting to the emergency room with true myocardial infarctions were disproportionately sent home with diagnoses like anxiety and indigestion. So we have to be very careful in how we design these things, that we don't just teach a model and bake our own biases right into the new system. Because what happens is somehow we can say stuff and we'll question it. When it's in a computer screen, the culture is not to question it. And here's a van that followed its GPS right off a cliff, just from local news at some time. So virtual truth is not always the truth either. And yet it's dangerous because the models could start to be better at certain tasks than the humans. So we have to think about, when the physician's, you know, gut instinct and the model's decision differ, what is needed? Do we need better validation? Do we need model explainability? How are we going to meet this challenge as physicians? Finally, deep learning is going to change what knowledge human physicians have to carry around in their head versus what they can look up. That can be good and bad. On the good side, if you're out in rural practice and you don't have experts nearby, you can have an expert decision on your phone or on your computer. Also, you know, pooled data, synthetic data, VR, robot simulations, and other tools could give physicians better training opportunities than they've ever had before. So there's definitely good to this. On the other hand, what we currently teach trainees to recognize patterns of disease may go the same way as physical exam and ECG interpretation, which is that we're not as good at it as we were before. And so the risk is, if we're not careful, our community might forget about what can be done with low-tech, low-cost data and homegrown neural networks. We had a physician from India come to Grand Rounds a couple of years ago. He showed a picture like this. He was an adult congenital heart disease physician in India. And he has the issue that when people want to travel to him for surgery or opinion, they are taking, you know, 1,000-mile journeys that are cost prohibitive to them. And there was a patient with an ASD who wanted to come see him for ASD closure. And he said, before you make this journey that you can't afford, send me a picture like this. And it's not good news, but he was able to say, don't come because this is Eisenmenger's and we can't close it. So there's value in low-cost, low-tech data. We can't forget that as we build these computational models. Multi-center validation. So some of the first AI models tried to find pathology on chest x-rays performed on a holdout test data set, but it fared poorly on chest x-rays from other institutions. And so we need to incorporate multi-center data into our models. This is adapted from Piotr Slomka's lab in Cedars-Sinai, who studies nuclear cardiology. And he takes this k-fold cross-validation approach, where each time he rotates his training and test sets and uses imaging from different hospitals. So this is one good way to do it. And to be able to rotate data across different hospitals takes not only sound research design, but also sharing data or sharing models, having shared pipelines for harmonizing data, and having a common platform to do these analyses. And that leads me to the last point, which is a word on infrastructure and collaboration. Because if you think a hospital is ready for data science just because it has data, that's like saying that this is a sweater. There's a lot of steps in between, and it takes an all hands on deck approach. I had to build a lot of our initial pipeline myself, not because I'm the best coder, but because everything we tried to do, there were no tools at the time that we did it. So we built these, and now I'm helping scale these across the institution at UCSF. We are building a UC-wide information commons where the entire universe of data from our EHR, including structured data, imaging, and everything, will exist in a de-identified state in the cloud for research. And we've envisioned an architecture or infrastructure for integrating deep learning models back into the imaging point of care, like into the CT scanners and MR scanners, et cetera. And that's being led by Dr. Sharmila Majmudar as part of the Center for Intelligent Imaging. So it's all hands on deck. All of this has required and is requiring an incredible multidisciplinary effort at several levels, breaking down silos and building communities and resources across some of the traditional clinical dividing lines. So this is some of the stuff that I've had to deal with, and we have to connect it. And that's what's going to lead us to progress at a scale that we haven't seen yet. So this is a summary. Image-based phenotyping has got to improve. Machine learning can help, specifically deep learning. We've made concrete progress on some specific use cases, but further advances are going to require a comprehensive multidisciplinary approach at a programmatic level. So I've talked a lot today, and there's a lot left to do. But for inspiration, I remember that medical ultrasound itself was a major advance in imaging, born of a multidisciplinary collaboration between a doctor and a physicist. And so with that, I want to thank my team, thank UCSF, which has been incredibly supportive, both the Division of Cardiology, the Baker Institute, the Center for Intelligent Imaging, my funding sources, and I'd love to take some questions.